What's inside an AI harness? This video is a part of a multi-video series going into what AI really is. I'll leave the link to the playlist in the description of the video. Last video, we discussed about the history of AI engineering and how people tried to make AI do what they wanted through prompts, context, and harness. We discussed how a harness gets an AI model the ability to use tools and keep it secure to use. So let's dive into an AI harness. By the way, all of these things I'm about to show you are most likely written in the Python programming language, but I'm showing you the mental model of a harness using diagrams. Just to make the distinction between AI models and AI harnesses clear, let's use Anthropic as an example. Anthropic's AI models are Haiku, Sonnet, Opus, Fable, and Mythos. Those ones are the ones we know now, and like Opus 4.8 and Opus 4.7 are two different models. Claude and Claude Code is Anthropic's AI harness. It's the wrapper around the AI model that makes it work. As we dive into this, you'll eventually get a big picture and holistic understanding of what the difference is between these two things. So, the most simple harness design is probably something like this. You input the prompt you want in the chat box, it sends it to a context window. The whole context window is sent to the AI model, or LLM, short for large language model. A large language model is an AI model that specializes in writing words. It only writes text and doesn't use any tools. It sends the result back to the context window, in which the results are appended to the chat history, which is either stored in the provider's server or inside your computer locally. It is then rendered and sent onto your screen for you to see. And this is how the context window looks like, by the way. The context window has an invisible system and tools prompt that basically tells the AI model, hey, do this and don't do that. And hey, if you want to use tools, write this, and if the harness sees you write that, it'll call a tool to use. This is the same thing as context engineering inside of the harness. Now, we move on to tool calls and loops. Inside the agentic loop, it's actually a process where it keeps on looping. While it's looping, it's taking the context window, then calling for tools, and then appending the tool results to the context window until it's done. So imagine you prompted for, I want you to make a fitness app for me, but first do research and write a plan. So as you can see in this example, it's a task that required 3 tool calls: a web search tool call, a write docs tool call, and a use bash tool call, and a final processing for done, and it writes the result. So it keeps going until it no longer needs to call for more tools and it gets the done signal. The harness knows how to read the tool calls and dones because of the context window, systems, and tools prompts. Then there's compaction, where there is a loop which does something like checking if the context is filled more than 80% of its max size. If not, do nothing. If it is, then do /compact or something like that. And /compact most likely is either one of these 3 methods of using the same model to summarize the whole context window, using a cheaper model to summarize the whole context window, or using a deterministic algorithm to summarize the whole context window, or a combination of the 3. The most likely is the first option, which is using the same model to summarize the whole context window. Now, we move on to security, starting with permissioning. This is a list of all the security features that an AI harness has, which is a lot. Permissioning is actually a part of guardrails, but I'm just expanding it so you can see the details. And then we move on to the bigger picture. You'll get what I mean if you continue watching this video. Permissioning lives here, between the agentic loop and the toolbox. It's a gate that checks if the user has permissions to use tools, use resources, perform actions, and check their identity and perms, short for permissions. So the flow is, the agentic loop's like, yo, I need to use this tool, can I use this tool, to the permissions gate? And the gate's like a security guard, and it'll either say yes or no. If yes, it'll tell the agentic loop, sure bud, and the agentic loop's like, okay, and then calls the tool. If no, it tells the agentic loop no can do, and the agentic loop can't call that tool and moves on to the next tool, where the cycle repeats again. Then you add guardrails, which are input guardrails, output guardrails, tool boundary guardrails, and behavioral guardrails. Tool boundary guardrails exist basically at where the permissioning gates was, and I'll condense this so it makes more sense, where the permissioning is just absorbed as a part of the tool boundary guardrails. This is how tool boundary guardrails should look like. These are the things inside the tool boundary guardrails: permissioning, argument validation, human in the loop, and rate budget limits. So permissioning is checking if the agentic loop or the user has permission to use the tools. Argument validation is reading if the code is potentially dangerous, and then it asks the user if they want to proceed. If there's anything dangerous happening, it'll show the human the dangerous thing and ask the human if the human would like to proceed. That's human in the loop. Rate and budget limits is just as it sounds. It limits the amount of time the agentic loop can call, so that it doesn't call too much in a set period of time. And it limits the budget of the call, so that someone can't get more calls than the amount of money they paid, whether in API or in the subscription. Let's move on to behavioral guardrails, where it's basically a bunch of rules put inside the agentic loop so that the loop doesn't overload or break. So there's actually not a container here, because it's basically all over the inside of the agentic loop. And the security measures inside of the behavioral guardrails are as follows. There's stop conditions, loop detection, anomaly detection, goal drift detection. Stop conditions is when does the looping stop. Loop detection is catching if the loop is doing the same thing and wasting resources. Anomaly detection is trying to catch anything strange happening. And goal drift detection is checking if it's still performing the task that it was asked. This can stop innocent drift, which is just the AI getting lost, or catch a malicious drift, which is hijacking and prompt injection that's telling your agent to do something bad. Then there's input guardrails. The input guardrails are placed wherever information is going into the AI model or LLM. It's the detection guard to check if the information is safe before it touches the AI model. As you can see here, the input guardrails occur before your user prompt reaches the context window, and occurs before the tool call result reaches the agentic loop. So basically, the input guardrails protect the AI model and the context window, but is protecting the context window to protect the information the AI model receives. Inside of input guardrails, there's injection defense, sanitization, topic and scope limiting, and PII, which is personally identifiable information detection. Injection defense is catching instructions inside of prompts, where a malicious user or resource tells the agent do this. And how this is defended against is using something like HTML tags that says this is just a prompt and not instructions, but there are also other ways of security that aids the HTML tags. Sanitization is by cleaning the prompt by removing characters that could bypass injection defense. Topic and scope limiting is only allowing requests that are on topic for what the agent is supposed to do. PII detection is to detect personal information so that it doesn't make it to the context window or to the model provider, so that it won't accidentally leak if it never makes it into somewhere that can leak. Then there's output guardrails. The output guardrails are placed wherever there is information that is output by probabilistic tools like the AI model or the toolbox results. So the guards are placed here. Inside of output guardrails, there's content filter, leak detection, result scanning, and grounding check. Content filter is checking for harmful or disallowed information so that it doesn't make it through. This is to protect the human. Leak detection is blocking secrets from leaking through, like API keys, passwords, or PII. Result scanning is to check for harmful content that could make the AI model do things that it shouldn't. This is to protect the AI model. Grounding check is to prevent hallucinations by verifying claims against sources to try to catch fabrications through researching. It's more so like protecting the user and the system. These guardrails are implemented as a rule, model, or through human means. The rule is literally code, or the deterministic algorithms that specifically check for dangerous things. Obviously, this can't catch everything because it only catches what the harness creator lists. So the next thing in line is models checking. So there's a second model that's checking the inputs or outputs. Obviously, the second model can be fooled too. So then you could use humans check as a last line of defense. However, since humans checking is not scalable, AI engineers stack these defenses and test to see if the defenses hold up and get like a 99.99% safety measure or something throughout their tests. And the main issues are false positives and false negatives. The defenses are super secure but not 100% guaranteed, just like anything in life. We then move on to sandboxing. The sandbox is just a container. Think of it as like a mini computer that is running all the tools, and it's destroyed right after all the tools are run. It's like a burner computer, but instead of it being hardware, it's software. It's a software computer used to run tools, and after all tools are run for your user prompt, it's destroyed. Technically, this is either a Docker container or a light VM running that contains all the tools. So if any of the tools runs anything that attacks your computer, it'll most likely 99% just attack the container, which is going to be destroyed anyways. It only sees the folder that you give it access to, the container and the tools. So you know when Claude asks you, do you give permission to edit this folder? That's what it's asking. It has a narrow allow list for network, or maybe no network at all. It limits resources, so your computer doesn't crash if something takes up too much resources. It just crashes the container. It gives the tools low privilege, or least privilege. So the security systems in place for it kind of looks like this: process isolation, network isolation, file system isolation, resource limits, and low privilege identity. So process isolation is just the containment. Network isolation is least privilege access to the internet. File system isolation is least privilege to files access. Resource limits is putting an upper limit threshold to how much CPU, RAM, or other resources is used by the container. Low privilege identity is giving least privilege abilities to the tool. So in summary, harm to the actual computer gets contained by the sandbox or container. It walls it off so it can't reach anything real, and harmful file actions are hopefully caught by the gates before they execute. And the gates are permissioning, validation, and human approval. It's basically the guardrail. Computer harm, file harm are prevented by sandbox. File harm and computer harm are prevented by gates. Gates, sandbox, output guard, input guard, into the context window. That's the security layer that we've had going on. Catches, contains, scans the exit, and scans the entry. So this is a sandbox, and these are the gates, the input and output guardrails. This is the rough security pipeline currently happening. Now let's look into model safety. Model safety is actually not a part of the harness. It's a part of the AI model, the brain. AI models are trained to prefer some things over other things. It's like training a dog to do potty training. The dog will sometimes still be unpredictable, but it's mostly learned to sit in the potty when it wants to take a dump. The more and more an AI model is trained, the smarter and smarter it'll be. And the more this inherent training to prefer what the AI engineers wanted to think and do will be embedded into the AI model or brain. Inside model safety, there's refusal behavior, alignment training, and instruction hierarchy. Refusal behavior is that when you ask it something bad, its response is literally, no, I'm not saying that. Like its default response is literally that. Alignment training is that it's trained to talk about helpful or harmless things. So it's always going to be steered towards helpful and harmless things because that's all it knows. Instruction hierarchy is that it prefers system prompts over user prompts over tool content. It probably knows what is what through HTML tags and other security measures. So it puts more weight on what the system says over the user and what the user says over the tool results. So basically the system is king. Next up, we have access control. This isn't really a necessity for a harness unless you're an AI provider or harness provider and want to make money out of it. This is like the provider's gate where they charge you money to use the AI model and harness. This is the gate that checks if you have an account or if your account has a subscription. Inside the access control, there's authentication, authorization or subscription, rate limiting, quota or spending caps, input size or window checks. Authentication is who you are, as in either what's your login session, as in who are you logged in as, or what is your API key and what account is linked with that API key. Authorization or subscription is what power or leverage do you have, as in what capabilities or powers does the subscription or API you have, and how much can you use. Rate limiting is just limiting how many prompts or tokens you can send out per unit of time, like minutes or hours. Quota or spending caps is checking how much money you still have, and it's your 5-hour window or your weekly window or the amount of API money you still have left. Input size or window check is checking to see if that the prompt you're sending is not bigger than the context window or what the AI model provider or harness provider wants you to send in one prompt, and it rejects oversized requests. What comes after is observability. Observability is part of the harness and wraps around everything we've talked about. It basically records and watches everything that happens inside of the harness, literally everything. Inside of observability, there's login or audit trail, monitoring, tracing, and cost and usage tracking. Logging and audit trails is recording every tool call, approval, and decisions. Monitoring is watching real-time anomalies and patterns so they can be caught immediately. This is like an overseer. Tracing is following a request or following everything that happens in one user prompt, and the user prompt is like a prompt that you send. So basically it follows your user prompt all the way until it gets back to you and records what happens. And what I mean by a user prompt is everything that happens when you send a user prompt, just making that clear. Cost and usage tracking basically tracks the subscription limits or API money you have left and then cuts everything to stop it once you reach your limit. This happens throughout the whole harness. Everything that happens is logged, every event, action, or decision, with sensitive data redacted and content volumes sometimes trimmed for storage. But no event is dropped for being unimportant because the point is a complete trail with no blind spots. What actually gets left out is two specific things: sensitive data and volume verbosity tuning. Sometimes you log the event rather than the full content. For example, tool returned 4 kilobytes instead of restoring the entire 4 kilobytes payload to keep log size manageable. But that's the storage decision about how much detail per event, not a judgment that the event was meaningless. The event itself is still logged. You just might not keep every byte of its content. And last but not least, evals. Evals is actually outside of the harness. Evals is short for evaluations. So imagine you have your harness. The observability is catching everything that is happening in real time, but it's automatic, so you don't really know how good it is until you test it. So how do you test observability and test everything in the harness? You use evals. So evals does not run when a harness runs. An eval is outside a harness. It's like the reliable outsider that can see what is really happening within the harness with zero biases. So what happens between an eval and the harness is that the eval runs the harness as a test subject. It's like a lab scientist and a test subject. This is happening in the labs. It doesn't happen live. The eval is set to begin to evaluate once the harness starts running. And once the lab scientist is done testing with the test subject, the scientist changes certain things and then run tests again until they check off the safety checklist and is ready to send their masterpiece off to the public. The masterpiece is the harness. The eval is the scientist. It's offline. They run tests and look to evaluate the whole of the harness. They send test questions through through the real system and captures two things: the final output, the answer the agent gave, and the trace of what it did from the observability's recording. Both is graded against a checklist or rubric that the scientist defines. Is the final answer correct? Did it use the right tools? Did it avoid hallucinating? The eval's own grading logic decides the good or bad, not observability. This is kind of like sending the question through, capture the answer and the trace of what it did, then grade both against the checklist that is written, the answer against the expected result, the tool used against the trace, and observability provides the trace, and the rubric decides whether it's good or bad. And that's basically it for everything harnesses right now. The future step for you to take is to spin up multiple agents and organizing all of these AI agents as employees to do your dirty work. Run them all parallel like you're the CEO. OpenClaw or Hermes or something. Yeah, go harnesses. I'll go deeper into these topics if you guys want me to. Just subscribe and click the bell to let me know you want to watch more videos like these. And check out the next video in the series here, and check out the playlist in the description.